Philosophy begins with the most basic of questions. Is this all there is? I think John Locke was right on Wednesday. Children are born with a blank slate. Whatever you write on it, it stays. They have a completely blank blackboard. How'd you learn language? You didn't study English, you learned it. People wrote it on you. They wrote it on your brain. And you would hear those vowels, you'd hear those diphthongs, you'd hear those sounds over and over and over again, and then you started practicing. And if you got it wrong, hopefully someone gave you a little bit of insight into how to pronounce it correctly. And before you know it, you were speaking English. I have a 3-year-old grandson. I was on the video phone with my son. I said, how's Parker doing? He says he's just words come out of his mouth every day now. For a long time, he was still trying to associate all the sounds that he was hearing. And after a while, it just happens to you. But you're not born talking. It's something that you get imprinted with. The same thing with knowledge. So as you begin to accumulate knowledge, you have questions. How does the world fit together? Why is it this way? Does it have to be this way? Is there any other way to look at it? Okay, so we begin with that presumption. The children are born blank. Children begin with perceptions and experiences. Access to reason doesn't occur until their late teens or early 20s. We call this abstract thinking. So when you're born, you have tons of perceptions. Half of your brain the first 6 months is dedicated to spatial relationships. Have I said that in this class yet? Your brain is working overtime trying to figure out that when you walk down the hallway and 100 yards down the hallway, it looks like it's going to get real slow. Your brain says, no, that's just an illusion. Don't worry about it. You look down a hot highway and it looks like a lake, and your brain says, that's not a lake, you remember? It's the heat coming off from macadam, and the atmosphere is real dense, and so the refraction makes it look like but it's really not a lake down there. And your mind is putting all of this together outside the classroom, just through life's experiences. You learn to put your shoes on, you learn to tie knots, you learn to do all those things. And it all begins with sensory perceptions and experiences, which is exactly what the empiricists talk to us about. Some things look good, they taste awful. Grandpa can take his teeth out, but they're not real teeth. The moon and mustard are both yellow, but the color yellow is not equivalent. It doesn't apply equally the same way. Parents who explain the distinction between appearance and reality are introducing their children to philosophy. You all went through this. I bet you all had little friends, little talking buddies, until they told you they're not real. You have to grow up and put those things away. I explained about all 3 of my young boy children at 2 years old wanting to know who made the moon, Daddy. Why would a 2-year-old think that there's something behind it rather than where did it come from? They begin with surface qualities and then move on to more essential qualities. A blue-green cup, or is it really a green-blue cup? The lake at the end of the highway. A cow eats grass and out comes milk. You know, kids wonder about that. There's a company in New England right now trying to produce cows that make skim milk, cut down the fat content. I'm waiting for chocolate milk. When I told you about Reggie Corliss, that fellow that I ran into that supposedly looked like me, and my son thought that he saw Uncle Jerry there. So philosophy provides us with a structure and a method for continuing to ask, is this all there is? In metaphysics, we started this the very first day we were in class. This is an example of macrophysics. But on a level below this, there's something called microphysics or atomic physics. And atoms are much different than the material that we see up here. And yet they're both very real. Is one more real than the other? And I asked you the question, how is it that I can sit on this table and not go through it? Because most of this table is just air. When I take an electron microscope and I blow up material, matter, I find out most of it is space. And it's made up of atoms that are mostly space. And they have these little protons and neutrons and these little electrons that run all over the place. And most of matter is emptiness. But I don't fall through this. It holds me up. If we dig down even deeper, we get to quantum physics, which is subatomic physics. We realize that everything is really about energy down there. And while this world is predictable, follows what we call the laws of physics, and the subatomic world, for the most part, is predictable. We find out in quantum physics, I can't tell you where those dumb electrons are going to be from second to second. They're just helter-skelter all over the place. Well, wait a minute. How can the visible, larger physics follow rules of physics, and yet the thing that undergirds it doesn't follow the same rules? It's a question we haven't answered yet. We're looking for what's called a unified theory. And then we get down even lower to it, and we get to string theory, or what we call multiverse theory. And we're pretty sure that this is real. Mathematically, we can prove it. Well, math doesn't prove the real world, but it at least gives us a structure through which we look at it. That being said, if you'll indulge me, let me give you a visual explanation of this.
Let's suppose that you're writing a really important email to a colleague.
Nope, that's wrong.
Or a post on Facebook.
Here's the new idea of string theory. Deep inside any of these particles, there is something else. The something else is this dancing filament of energy. It looks like a vibrating string. That's where the idea of string theory comes from. And just like the vibrating strings that you just saw in a cello can vibrate in different patterns, these can also vibrate in different patterns. They don't produce different musical notes. Rather, they produce the different particles making up the world around us. So if these ideas are correct, this is what the ultra-microscopic landscape of the universe looks like. It's built up of a huge number of these little tiny filaments of vibrating energy, vibrating in different frequencies. The different frequencies produce the different particles. The different particles are responsible for all the richness in the world around us. And there you see unification, because matter particles, electrons and quarks, radiation particles, photons, gravitons, are all built up from one entity. So matter and the forces of nature all are put together under the rubric of vibrating strings, and that's what we mean by a unified theory. Now here is the catch. When you study the mathematics of string theory, you find that it doesn't work in a universe that just has 3 dimensions of space. It doesn't work in a universe with 4 dimensions of space, nor 5 nor 6. Finally, you can study the equations and show that it works only in a universe that has 10 dimensions of space and 1 dimension of time. It leads us right back to this idea of Kaluza and Klein that our world, when appropriately described, has more dimensions than the ones that we see. Now, you might think about that and say, well, okay, you know, if you have extra dimensions and they're really tightly curled up, yeah, perhaps we won't see them if they're small enough, but, you know, if there's a little tiny civilization of green people walking around down there, you make them small enough and we won't see them either. That is true. One of the other predictions of string theory. No, that's not one of the other predictions of string theory. But it raises the question, are we just trying to hide away these extra dimensions, or do they tell us something about the world? And the remaining time, I'd like to tell you 2 features of them. First is, many of us believe that these extra dimensions hold the answer to what perhaps is the deepest question in theoretical physics, theoretical science. And that question is this. When we look around the world, as scientists have done for the last 100 years, there appear to be about 20 numbers that really describe our universe. These are numbers like the mass of the particles, like electrons and quarks, the strength of gravity, the strength of the electromagnetic force, a list of about 20 numbers that have been measured with incredible precision, but nobody has an explanation for why the numbers have the particular values that they do. Now, does string theory often answer? Not yet, but we believe the answer for why those numbers have the values they do may rely on the form of the extra dimensions. And the wonderful thing is, if those numbers had any other values than the known ones, the universe as we know it wouldn't exist. This is a deep question. Why are those numbers so finely tuned to allow stars to shine and planets to form when we recognize that if you fiddle with those numbers, if I had 20 dials up here and I let you come up and fiddle with those numbers, almost any fiddling makes the universe disappear. So can we explain those 20 numbers? And string theory suggests that those 20 numbers have to do with the extra dimensions. Let me show you how. So when we talk about the extra dimensions in string theory, It's not one extra dimension, as in the older ideas of Kaluza and Klein. This is what string theory says about the extra dimensions. They have a very rich, intertwined geometry. This is an example of something known as a Calabi-Yau shape. Name isn't all that important, but as you can see, the extra dimensions fold in on themselves and intertwine in a very interesting shape, interesting structure. And the idea is that if this is what the extra dimensions look like, then the microscopic landscape of our universe all around us would look like this on the tiniest of scales. When you swing your hand, you'd be moving around these extra dimensions over and over again, but they're so small that we wouldn't know it. So what is the physical implication, though, relevant to those 20 numbers? Consider this. If you look at the instrument, a French horn, notice that the vibrations of the air streams are affected by the shape of the instrument. Now, in string theory, all the numbers are reflections of the way strings can vibrate. So just as those air streams are affected by the twists and turns in the instrument, strings themselves will be affected by the vibrational patterns and the geometry within which they are moving. So let me bring some strings into the story. And if you watch these little fellas vibrating around, they'll be here in a second right there, notice that the way they vibrate is affected by the geometry of the extra dimensions. So if we knew exactly what the extra dimensions look like, we don't yet, but if we did, we should be able to calculate the allowed notes, the allowed vibrational patterns. And if we could calculate the allowed vibrational patterns, we should be able to calculate those 20 numbers. And if the answer that we get from our calculations agrees with the values of those numbers that have been determined through detailed and precise experimentation, this in many ways would be the first fundamental explanation for why the structure of the universe is the way it is.
Now, what difference does that make? How many are going to be physicists after this little lecture? One. Okay, that's cool. Two of us, but I'll be practicing, you'll be performing. What difference does it make? Well, my father died, my brother, and this might be deja vu. My brother came down here. We had to settle some things up, and we went out and had breakfast, and while we're out there, he says, hey, I got a question for you. This is a guy with 135 IQ. He's not dumb. He says, I was watching TV last night, and they're talking about this thing called string theory. Do you understand it? I said, well, the math is above my pay grade, but yeah, I understand the theory and the philosophy behind it. Why? And he goes, he's very practical. He was did I say this? He was very high up in Chase Manhattan Bank. He was in charge of the year 2000 computer possible crash because the numbers wouldn't roll over past 1999. He was in charge of all of it for all the worldwide Chase Manhattan. This guy's a bright guy, but he's very nuts and bolts. He says, what's it good for? And I said, nothing. He kind of looks at me for a minute like, I said, well, let me ask you a question. I said, do you know where steel-belted tires come from? I haven't talked about this in class, right? Did I? In this class? I have one. Anybody else remember? No one else remembers? That's cool. Maybe, okay. I said, because when we went to the moon, see, down here on the Earth, everything's regulated by weather. And weather has a kind of smoothing effect. So things are kind of smooth on their edges for the most part. There's certainly sharp edges and whatnot, but most of it is smooth. But in the moon, there's no atmosphere, and we weren't sure if there were rocks or whatever, and they'd be sharp as razors. What happens to a tire when you drive over something sharp